Hey everyone, welcome back to the 443 Security Simplified. I'm your host, Mark the Liberty, and joining me today is
Corey ChatJCN Knockreiner, ready to learn about AI.
that's a
You
deep
don't know
cut.
my initials? JCN?
That's a good point.
Some people don't
Anyways,
know my first name.
as you might have noticed for the folks watching this episode instead of just listening, we are joined by a guest as well. Luke Wolcott is the head of MDR data science at WatchGuard. And as Corey just hinted at, we brought Luke on to chat all about AI and machine learning and some of its applications in cybersecurity. So Luke, yeah, thank you for hopping on.
Hi, thanks for having me.
Cool. So let's go ahead and roll our way in. Anytime we have a new guest on the podcast, we like to ask them a question of what is your hacker origin story? So really, like, what got you into cybersecurity, or at least got you to where you're at right now, working pretty heavily in cybersecurity and AI machine learning?
So the short answer would be, as a kid, we watched Sneakers, R.I.P. Robert Redford. Loved the movie and just got so excited. Thought that was super cool. And then someday when I had an offer to have a job working in cybersecurity, I was like, oh yeah, it was meant to be. It's all because of that movie Sneakers. The longer answer is I went to college for math and physics and took a year off from college, went to India, got really into drumming, realized that I was really into North Indian classical music, kind of developed this pattern of just getting really obsessed about something for a while and trying to find the most complicated, arcane topic, and then just like get obsessed and focus on that. Went from North Indian classical music and like bumming around India back to college. And then I went back to India for 2 years. And then I got into like traveling around the world. At this point, I've gone to 75 different countries, mostly by doing these long, like overland trips, trying to be as frugal as possible. Obsessed with that, just focused on like, how do you live on a shoestring in other countries? Ran out of money, decided that my brain was hungry, and I went to grad school for math. 6 years, got a math PhD in the most useless esoteric topic I could find, which is tensor triangulated category theory, which is an area of algebraic topology. I'm sure it doesn't matter what it is. It was just like proofs and theorems. And after that, 5 years in academia, did a postdoc, worked as a math professor for a while, got really passionate about coding, data science, taught myself data science. In 2017, switched from academia to tech, and then spent 3 years in healthcare IT, like doing data science for healthcare. And that was really cool because one of the most, made a list of like the most complicated things. United States healthcare system is on that list.
Yeah.
And at least for a little while, I understood how Medicare works and how Obamacare works.
Wow.
It's like, what's the most complicated thing? And obviously the internet and, computers and stuff. So I was excited to move over to cybersecurity. I just love how, I guess, when I think of what does it take to be a hacker, you have to be kind of obsessed about like really esoteric, detailed minutia, and that sort of gives you magic secret power once you are.
I agree. Yeah. People that want to deep dive on any sort of technical or scientific topic, the level of deep dive you get gives you that magic. I love it. By the way, I think Sneakers, among with like War Games and Hackers, are common movies for all of us. Sneakers is one I love too. I think it's more a pop culture version, but there is a lot of hacking. And my memory is that also was the first time they showed a failed Newton in the movie. Remember the Apple Newton, the first PDA before even Windows CE came out? One of the sneaker guys was on a train and was using a Newton for a hack. So that's my weird memory of Sneakers. That sounds like awesome history. We're glad we got you here in cybersecurity.
That's super cool. Do you have a travel book you've authored yet?
Maybe.
Ooh.
I was also
We'll have to
interested
go
in the
find that.
drumming, by the way. Mark, like drumming is one of my hobbies. I'm not great at it, and my kit's in storage right now. But besides the Indian drumming, do you do traditional rock kits too, or?
Not traditional rock kits. I mean, I have some sort of things on Bandcamp and Spotify if you want to go hunting
Fun.
for them. But yeah, I mostly got into like whatever, like world rhythm traditions, and also decided that North Indian tabla was the coolest. I think South Indian rhythm is officially the most complicated rhythm system in the world, and North India is what I would call second. So,
Wow.
Man, that's awesome. Here, I thought we were going to talk about AI, but I'm actually wanting to go more down this rabbit hole instead. But
I mean,
AI can improve all of these things.
When I left college, I like, well, what are you going to do when you graduate from college? I applied for like Fulbrights and like these fellowships to go study music, and I got none of them. And I was like, oh, I guess that's the end of my music career.
dang. Well, that's awesome. So long journey to get you to where you're at right now. But I guess like real quick before we dive in, you want to give us a quick overview of like what you're responsible for right now at WatchGuard?
Yeah. So WatchGuard has a business unit devoted to MDR, managed detection and response. We have a SOC, and we sort of, this is like a wraparound cybersecurity service, all the different platforms, all the different everythings for small, medium businesses. And so I'm in charge of the data science team there. One of our mandates, we've got two mandates. One is to just do whatever cool AI stuff we want to and can think of. And so for like over a year now, we've been making these AI agents to help automate SOC workflows. And that's just like obviously super cool AI agentic workflows. And then I spent a lot of time working on this model called Sixth Sense, which we'll probably talk about more, which is like I would say a interpretable multimodal foundation model for cybersecurity. Basically use it as an anomaly detector. And so that's sort of, I love just like connecting new data sources to that, working on that. That's one mandate. The second one is to kind of oversee the health of all of our detections. So the MDR service, we have detections for endpoint and cloud and identity and like mobile network. I think 236 detections in service last time I checked. All of those have to be like high signal, low noise. We checking on them, making sure if something goes wrong or we need to update them. And we add more all the time as well. So that takes quite a bit of work.
That's super cool. So right now, like we've talked about AI on this podcast a ton. Lately, we've been focusing a ton on like chatbots and agentic AI, like you mentioned, like little AI-based helpers that are great at certain tasks. But that's not the only form of AI. And so I wanted to start by spending some time talking about that second mandate that you were talking about with more traditional machine learning models, or AI models, if you still want to be marketing buzzwordy, and like how they eventually evolved into maybe the LLMs and the more powerful, but or at least larger models that people are more familiar with right now. So I guess like you want to start by giving us an overview of some of the different types of AI and machine learning and how traditional ML differs from LLMs?
I think this is it's a fascinating phenomenon that like maybe someday people are going to forget that there's like other types of AI that's not like the chatbots and stuff. But in industries like cybersecurity, I think like the non LLM based machine learning and AI is actually the most powerful, most useful. So, at the start of any kind of machine learning would be like, train a function using data to learn patterns in the data. Like you've got like a, XY plot, and there's some points on there, and you say like, what's the line that best captures that data? Like y equals mx plus b. And there's an algorithm that sort of helps you, actually in that case, there's a formula, but either a formula or algorithm that helps you like capture exactly, this is the best fit line for this data. And so that's statistics. It's been around for a long time, and there's a lot of different variations on that, like build a decision tree that captures the logic of this data set, put the data points into like a new space and then figure out what kind of like slice you can put, draw through that so that like, all the yeses are on this side and all the no's are on that side. That was all like what data science meant until like the 2000s when add to that an algorithms related, or like broadly called neural networks or deep learning, and that's like a particular type of connecting nodes with activations, and it's very, very, very powerful for like computers to train these things, because it's basically just addition and matrix multiplication, things we can do fast. So there was sort of a deep learning era, and then in 2017, a very specific type of neural network architecture was sort of discovered, called attention, and it was built into this thing called a transformer. And this just, again, was a complete revolution. It's just a very, very powerful way of connecting these nodes in a neural network. There are many, many other ways of connecting nodes, but this particular way, which is a transformer, is just super great because you can scale it out. You can just like pump more and more data into it. You can kind of like grow the size of this, and the model just like eats up the data you give it. And it's very parallelizable, and great for the types of chips we use to train models. And so for that sort of was this explosion of the start of like the modern AI era. And then that kind of went from 2017 up until 2022, I think it was, when ChatGPT came out. And the difference there was like, in addition to training the transformer on all of the internet's data, they also kind of discovered some really powerful post-processing. So you initially you pre-train it on the internet, and then there's another phase where you do the supervised fine-tuning on like question answer, and then there's another phase where you do this reinforcement learning. That basically the result is you have a chatbot who's good at question and answering, who knows the whole internet, and who talks like a human. And that's like the three pieces that came together to make ChatGPT, with which everything since then has sort of been based on. So everyone's just distracted talking about how amazing these LLMs are, because they're amazing. It's absurd how much money is getting spent on these things. It's absolutely absurd. I would like to just remind everyone there's a whole tranche of powerful models that are neural networks that have nothing to do with, text or ChatGPT.
Or generating images or video.
Sorry, what was that?
Or generating images or video, all the
right,
things.
Yeah. And then there's also like all these other algorithms that we could broadly call everything traditional ML at this point, because it's everything else is.
By the way, how much does this like? I've heard definitely ML, but I think even though AI is lots of pieces of ML put together, AI, I've heard it described as statistics at scale. And when you think of the math of some of these models, right? Yes, the tensor, how we're making the math fast is complicated, but the model, the math itself, statistical math, have existed for a while. So what I'm getting at is, how is the scale really the magic here? The fact that with compute, we can give a model so much data that it can do right things more often. Like humans always have to make yes or no, right or wrong decisions, whatever the decision may be, or whatever we say in our brain all the time. And we're building off the data we have from our history and our memory. But what's different here is big data. Is that true or false?
Right. Yeah. No, I think that's it. And there's sort of a creative, the way that the neural networks are linked together is kind of also part of the magic. The fact that there's a sort of attention layer that does a certain effect where like the input data can kind of learn what's important. What does it need to attend to in the input data? And then followed by a certain block of a different type of structure, and then followed by another attention layer, and then another block. And so it's like all of it, these things are wired together in a very special way. But yeah, if you think of the example of a line that's like mx plus b, the parameters there are the slope m and b, the y-intercept, right? I think you all remember that. There's two parameters there. And so you're trying to find like this line, and there's two parameters. Well, modern day models have not two parameters, not millions of parameters, not billions of parameters, but sometimes trillions of parameters. And that's a capacity for storing information that's like, hey, I know the internet, give me more, give me another, keep coming. You guys have to make more content so I can absorb it,
And the parameters, as it were, that humans are making decisions on are the ones we think are important. But I think we'll get into this question later, so I won't spoil it. But even knowing what parameters are important, or I think in some models,
Right.
unsupervised it's neat how AI adds that. But before we get there, essentially you pointed out that traditional ML, some of the normal machine learning we're doing has already big values in all kinds of industry that may not be realized. But can you give us a few solid examples, even if we have to use, I'd give general ones too, but even in our product, how traditional ML is applied in
Right.
security today?
Yeah, so a good example of like a very basic, simple thing that I would call ML is like, if in security, if you're interested in a particular parameter and you want to alert when that parameter is abnormally large, whatever that means. So the amount of traffic leaving a certain IP address, going wherever, day to day, there's a certain amount of data going. Let me know when there's a spike, right? So this isn't an awesome detection because it might go off quite a bit, right? But it's like a simple example. And so your parameter there is like, amount of data leaving every 5 minutes, and you just check every 5 minutes and look for a spike. You have to learn what's normal. So you take some training data and you say, okay, let's use that as our training. Okay, now we know normally there's a distribution of like the amount of data leaving. And then I just sort of my detection here is just, anytime in a 5-minute period, there's a, 99th percentile or 99.99th percentile, then generate an alert. So that is like a super simple machine learning model because you learn on data and you can relearn as the data changes, and you have a function that alerts in a certain scenario. So that's what an ML model that gets used in cybersecurity. We have a bunch of those. Like I said, they're not the best because they're kind of naive. They're just looking at a single parameter. If you take, a few dozen different parameters like that, like, what countries does this person normally log in from? And, what time of day is it? And stuff like that. You can use those traditional ML models. I'm thinking of a model we have that's for like detecting a botnet attack or like a brute force attack. It has maybe like 25 different parameters. The algorithm is called a random forest, and we trained it to basically go off whenever there's we think there's a successful botnet attack that resulted in a successful login. This has been in service. We've been using this for years now. It evaluates every single login, O365 login, and there's like quite a few of those. People are logging in a lot. And it is so high fidelity that we, when it does go off, send it directly to the customer. The customer can configure it so that to like automatically disable the password, kick the user out and reset their password. So that's how confident we are about the quality of this detection. And it's because it pulls in these 25 different signals. So that's an example of a purely traditional ML random forest model that we have.
Cool.
Yeah. So you work every day in building and maintaining these machine learning models at WatchGuard, and a big piece of that is actually managing the data to train them. And Corey's mentioned it a couple of times. You've mentioned it a few times. These concepts of supervised versus unsupervised training for models. Can you maybe quickly walk us through like those terms and what it actually means, what some of the benefits are or trade-offs are for each of them?
Yeah, and this is, I think, extra relevant to cybersecurity because, data. I talked to my friends who are data scientists. They work with other types of data, and I'm kind of jealous of them because they have all this labeled data and they can do all these supervised algorithms. In cybersecurity, you don't, the type of labels you would want, you don't always have, or they're very skewed, right? Because it's like an attack is a true positive, and then everything else is just like normal, not attacks, and so you don't have that many examples of attacks, fortunately, to build a model that's like go off when there's an attack, right? So a supervised model is where the training objective, the sort of task you're giving the model to learn on, is explicitly like these labels of, is this a cat or a dog? Is this an attack or not an attack? And like I said, in cybersecurity, you don't always have that data. You can create it. For example, the model I was just talking about, this botnet attack, we don't have a lot of successful botnet attacks, but everyone everywhere is getting botnet attacked. I mean, there's just like, that's the internet, right? And so you can synthesize true example, like, positive cases by just saying, okay, suppose this failed botnet attack was actually successful. And all you have to do is like switch one of those failed logins to a successful login and kind of randomly sample which one you're going to do. And then you can basically convert your useless unlabeled data by kind of synthesizing these positive cases. So now you have a bunch of examples of successful attacks, a bunch of examples of unsuccessful attacks, and your model can learn to kind of distinguish. So that's a way of kind of creating a supervised situation. If I didn't say it, supervised is where you have labels that are kind of explicitly what you're working for. I do know
it's a simple way to maybe point that is the humans have probably recognized the parameters that they think are important to making a decision and are actually using those parameters. Is that, I know I'm taking it high level and may make it less tech, but is that true or not?
Yes, but especially that we have the sort of the outputs of like
you have enough training results to know that.
Yeah, we're trying to get the SOC to create data. So like, this is the type of thing you would escalate, and this is the type of thing you wouldn't. And so the SOC we're like taking their brain computation and saying,
what I'm kind of getting at is you mentioned the dog cat example, and like how a human would identify a dog or a cat would be, I already know a cat tends to have pointy ears and the dog tends to have curved floppy ears. So that's a feature I would look for as being a higher weight for a cat if it were triangular. And I'm curious, in a supervised, I assume the SOC is helping pick the parameters that help show an attack. But I also know that to identify dogs and cats, sometimes the unsupervised model doesn't know what an ear or like it's looking at pixel level, like literally binary data that a human may not identify at all. Does that play in both supervised and unsupervised model, or is essentially supervised is we're helping pick the parameters that we think are important?
So what the difference between supervised and unsupervised is not like how the features are come about. It's specifically like, do we have labels for the data that we're training on? So the distinction would be, do you have a bunch of pictures that say cat, dog, cat, dog, cat, dog?
Gotcha.
Is that whether the features that the model learns are sort of engineered by hand or just sort of bizarre pixel patterns is different. But I mean, it is usually the case when you have a supervised model that you want to have these interpretable features behind the scenes.
Okay.
So what unsupervised is that you don't have that labels, and you're just sort of saying, here's a bunch of data, try and learn what you can learn. And so what you end up usually doing is creating like a proxy task. So in the case of text, if I just give you a bunch of text, like here's the internet, learn how humanity works. The proxy task is to like predict the next word in the sentence, as you probably heard with these LLMs. And that's hard to do unless you create this whole, either memorize all your content, which they do first. And then once there's too much content, then they have to actually learn how does English work or how does the language work. So in cybersecurity, we do that with you. Since I said we don't usually have the labels of like, what was the outcome here? We never know the true negatives that we missed attacks. We don't like know the things we're missing all the time. But I do have a ton of data. So an unsupervised model there is like, so the Sixth Sense model is an autoencoder. And what it does is I give it whatever data, just normal data, any data from everywhere. It's trained on 5 months of all of our customers' data that comes from all the different assets. I just pump it through this thing and I say, your job, that your proxy task is to take the input data, compress it down into like a smaller space, instead of a 3,000 length vector, you want to make a 250 dimensional vector. And then you have to decode it, like push it back out in such a way that like you've compressed and then decompressed, and your proxy task is that you've like reconstructed the original. So kind of a weird thing, right? Like compress then decompress, and I'm going to score you on how well you did at reconstructing the original. But this is what an autoencoder is, and it has lots of applications for lots of things, and I'm using it as an anomaly detector. But it's an example of an unsupervised model. You come up with this other task, and the power of it is that now I can train on, like I said, all the data we get, I can train on it. I don't need someone to be like, this was a good endpoint.
Here's this type of data. Yeah. Okay, cool. I have a follow-up before I ask you my real question, but just as we're talking about the different models and supervised versus unsupervised, there's a lot of talk about adversarial machine learning. And I think the reason I kind of got into the difference between features and parameters is, my basic understanding of adversarial machine learning, if we use the cat dog example, for instance, is if there are patterns that have been discovered by non-human that don't like, let's say I could take a picture of a cat and I know it's a cat, but I could put a little sticker in the picture with the cat that looks like it just has random noise, and suddenly AI thinks it's a dog. That has happened. That's an example of a Google research paper. And my understanding is the adversarial machine learning, by being able to hook to a system that could both see the inputs of the questions being asked of the model and the outputs of the result, could, over a long period of time of just seeing that over and over, could start to figure out some of the underlying features that the ML model was looking for to make a decision of yes or no, let's say. How can you tell us a little bit more about adversarial machine learning? And is it something that it's pretty easy to understand in a cat and a dog picture, where you just have to add a little sticker that keeps the cat picture different, but it keeps the cat picture there, but when we're talking about network packets and technical things that, it has to still follow the standards of a network packet, is it realistic that adversarial machine learning could trick some of the security-based ML models? For instance, could they find things where they could trick anomaly detection by, while still carrying out a viable attack?
I think so, because I think that attacks can be very as convoluted as necessary to evade. That's what you're doing when you're attacking, is you're figuring out, you try something until you're blocked, and then you pivot and you try something, you're blocked, and then you're trying to evade and get in. I think so. It's actually a good example. I've already introduced like this, like random forest botnet attack versus the 6th Sense model. So the random forest botnet attack, you could definitely evade, like by doing this sort of like, poking at it and figuring out, because I said there's 25 features. They were created by humans, and they're kind of the obvious ones, like, oh, is it a normal time to log in? Is it a normal location to log in from? And so an attacker could figure out what we're looking for and fly under the radar. Definitely. Because like you said, there were humans making these features and basically putting together the story of what a botnet attack we think a botnet attack looks like. And you can evade that. With the 6th Sense model, first of all, there's a lot more features that it collects: weak signals, very weak signals, medium quality signals, high quality signals. We just dump everything in there. There's thousands of features. I'm not going to tell you what they are because I don't want anyone evading them, but they're on the endpoint, they're focused on this sort of living off the land activity that is super hard for more naive detections to detect. It's the kind of thing that a sophisticated attacker uses because they know they can get away with it.
PowerShell is something admins use. So how do you differentiate good versus bad?
Right. And then, the sequence of, when you run the different living off the land binaries is something you can manipulate. And so we have constructed this anomaly detector in a way that's like,
stupid Siri. Speaking of AI and machine learning gone rogue.
Don't call, just hang up on. So things that 6th Sense has going for it is that it is unsupervised. So it's learning patterns that even I don't know. I couldn't explain to you why it thinks that such and such is anomalous. And that's very powerful. All it knows is I gave it a bunch of normal data. It knows what normally happens in a small, medium business's customer network. and when it sees something that deviates from that. So yes, you're using PowerShell, but you're using it in a way that's not the way that
Not the
PowerShell is
normal.
used. Now that's really hard to evade, right? Because if you want to be an attacker, you kind of do have to use PowerShell in a way that's
Exactly.
not meant to be used.
Yeah.
So the power there is like, and we can like, the Sixth Sense model can serve almost as like a threat intel, where we pick up on attackers using things in new ways, because we're seeing the whole signal. And like I said, it's interpretable. When the anomaly score is high, it tells you which of the features it flagged as being surprised, was surprised by these features, this collection of sequence of events. So it is much more robust to the adversarial attack, especially because we designed it to pay attention to all of those super weak signals that you normally
Awesome. Cool. So there are ways to basically harden even against, maybe never completely prevent, but harden against adversarial machine learning.
The flip side of that is like, if an attacker, if I told them the secret, then they would know how to.
Of course. Yeah. The whole point of adversarial machine learning is probably to figure out the secret, but if they don't have the inputs and outputs. But moving on to the real question, you mentioned it yourself. There's so much freaking money being thrown into AI. OpenAI estimated it cost them between 1 and 2 billion just to train that latest model they released. Has it been 3 weeks or a month? GPT-5. And we hear just how expensive it is to train these LLMs in data centers full of GPUs and just the power. So it makes you think, oh gosh, it costs way too much and we have to kill the earth just to use an LLM. Is that the case with all the models we use here at WatchGuard? Are there cases that you're working on, are cases where at a high level, there's cheaper ways to leverage AI that still have huge value?
Yes, absolutely. This is the phenomenon of like the LLMs are just sort of sucking all the oxygen out of the air, and people are forgetting that there are these very useful applications. So the models that we have sort of retrain themselves on some frequency, like once a week, once every 2 weeks. Those retraining jobs cost a few $1,000s. So we'll see a little spike of a few $1,000s. It's not cheap, but it's not horrible.
It's not the billions we hear about for sure.
Right. This Sixth Sense model that I train, a lot of the computation is in engineering the features that go into the model. The model itself, I would say, is like relatively small. So whereas your ChatGPT or GPT-5 might be, 1 trillion parameters, the Sixth Sense model, it's a completely different paradigm. It's not doing text. It's like around 100 million parameters. So 100 million is a lot less than 1 trillion. Another example of like small models are not bad is like robots, like when you're watching the videos of like the robot folding the clothes and stuff, they have a model that's like a vision, computer vision, convert image into numbers. And that is, tens or hundreds of millions of parameters. And then the actual like model that they train to tell the robot how to move, there's only like a few thousands or millions of parameters, very small, very tiny. And training that is like free.
This is just a weird question, by the way. I recently saw the robot folding clothes, and on one hand, it's amazing and scary, but it was still, it's still slower than a human. I imagine in a year from now, it'll be faster. But what I'm getting at is the slight additional dexterity and nuance the robot will need to perfect instead of just flipping the fold and to actually use smaller movements. Is that going to exponentially increase the size of the model, or will that be smaller than we think? Like, is it the nuance of getting more human like what do they call the uncanny valley to beat that will take the extra effort?
I think so. Yeah. I think the reason that it's like every little like the like n+1 step of that model is like, tell me how to move, right? And so if you can move in 1,000 different ways by like you've got all these joints and stuff, that's fine. If you can move in 10,000 different ways because you're like a ballet dancer, then that's 10,000
harder.
10,000. So yeah, it does.
I'm wondering if that last 5%, because if I think of dictation software, and I've been using Dragon, like in the past, it's been 80% there for like multiple decades. but anyone that tries to use it every day knows that 80% is nowhere near good enough for grammar. And the last 20 years is just tiny little minute changes that gets it. And by the way, I still don't think it's usable. I still, voice dictation messes up when I'm texting. So I'm just wondering if what you're saying is low cost models are viable and get lots of good results, but is it really chasing that last little bit that really gets something there that has to have that increased cost? Or
I don't think not necessarily. I think there are definitely scenarios where with a finite
every
size
task is
model,
different. Yeah.
Past, those models are really good at playing chess and checkers and Go, and it's like we didn't have to hit any exponential wall there. We just plowed past the humans, and now
the reinforcement model beat Mario with the highest score way faster than any human. So and that did not. Someone did that at home. So
what the heck is Dragon Naturally Speaking's problem then? Why can't they actually make functional software, do you think?
Oh, I'm not blaming them. They're just an example of when I thought they were awesome the first time they released it. Now it's
I thought it was what was it, back in the early 2000s when it first came out, and it felt like wizardry that you could just talk to your computer. But even then, it was still like a specific set of keywords, like computer, open email, write message, send to Corey, period, hit send.
Exactly.
I had during COVID, I had a side project of making myself a little voice activated meditation bell. It's right over there. It's I got a Raspberry Pi, and
fun.
Most of it's just a timer. I have this cool old school switch built in that I flip it, and then after 30 minutes, it manually swings and hits this gong because I like the nice gong sound. Anyway, I was
analog. Don't. By the way, that's part of your hacker story. The second you mention I'm doing personal custom projects with a Raspberry Pi,
to ring a gong.
Every listener. And the fact that it's this total analog situation and you're over engineering. I love it.
Cardboard box, and it's got a little display that says stuff. If I flip it down, it's for me. It's the meditation gong. If I flip it up, it's for my partner, and he can put his finger on it, and it does his heart rate and breath regulation and stuff. Anyway, I was it shouldn't be that hard to make a voice recognition, where if I want more time, I say some keyword like continue, and if I want to just call it good, I'll just say stop. It was from scratch. It's hard to do a voice recognition thing. I didn't try that hard, but from absolute scratch, where you're generating your own training data and stuff.
Cool.
Yeah, it is super hard. I tried to do a similar project with my home assistant stuff and finally gave up. And as soon as OpenAI released an API to do a bunch of that, I just gave them $20 a month, and less of a personal gain, but at least I got a functional voice activation stuff at home that isn't stupid Alexa or Siri.
Yeah.
But so another question I had though, when it comes to training these models, and ideally you've got supervised data in most cases where you can definitively say hack or not a hack, whatever. When it comes to the actual capabilities of these models though, what considerations do you give to signal versus noise? How do you decide when it is a good model with regards to false positives versus true positives? Because I'm sure there is some fine line that you have to stay balanced on for those between effective or no false positives, but it'll literally never detect anything.
Mm-hmm. Yeah. I always hoped that the answer would converge to some sort of beautiful mathematical formula where we could just pick, because in past, in the healthcare job, we did that. We automatically learned what's the threshold. Oh, the threshold is 0.457, and that should be the value for this, and that'll maximize and optimize for this particular metric. We should do that. You could do that. In theory, I think. I think that the models that I know the endpoint team, right? We have the WatchGuard EDR product, has a ton of machine learning on device, in the cloud. Super cutting edge stuff. A lot of it's traditional ML, not transformer based. Some of it, they have a couple deep learning models running. Anyway, they are constantly tuning and paying attention to. They do have an optimized metric that they work towards. Because they have this zero trust attestation thing where every file that runs gets evaluated, and if they're not confident, it gets into their team of humans and stuff. So you should ask them that question, because they would have a very impressive answer. I know that. In terms of our MDR suite of detections, the way I think of it is very much end to end. So this is something that comes up when you have these models. It's like there's the task that the model was trained on, right? Which could be kind of silly, like predict the next word. It could do really good at that, but like, what do you actually care about, right? Like, so having metrics that are targeted towards what really matters is very different than how the model is trained. So the way we approach our detections is very much end to end. We have a SOC who's reviewing these and helping the customer to respond to these. Every detection we put into service has to have a low false positive rate, or else we just don't put it into service. So in some ways, that is the decision tree is like, can we make it so it has a low false positive rate? Now, what do I mean by that? Acceptable false positives is 3 false positives per month per customer.
Okay.
Or it's a larger customer, per 500 endpoints, because we kind of keep track per endpoint. So it's very explicit, and I calculate this every month for every detection for every tenant we have. Did it have the acceptable a number of false positives or not? And if not, then we need to fix it. So this is like, I would say our decision is, first of all, is this detection acceptable in terms of its low false positive rate? Now, the reason we care about that is because if something is going off too much, it's not really a detection anymore because of alert fatigue. Like, they will just ignore it. Everyone ignores it. So it's not like, oh, we have a noisy detection. It's like, you don't even have a detection. No one's looking at it. So low false positive is like so fundamental to our business. And then we just sort of keep adding on more detections. I think of it as this sort of like sparse mesh of detections that cover as many possible things as we can in the MITRE framework or whatever, MITRE matrix. And then our sixth sense model is this backstop where if there's something that's too noisy, we just add it to there. So it sort of becomes this like catch-all backstop that allows us to take this approach. In terms of like false negatives, I think we would say also we never want any false negatives, which is like, an attack. But that, again, is a sort of an end-to-end thing. So we do these RCAs and we look at like, where did we go wrong that allowed the attacker to get all the way over here, and how should we respond? So we do, debriefs and RCAs on all of our incidents, all of our major incidents, and almost always it results in making more detections. The result is that, it seems to be working. We have a suite of low noise, high signal detections that are manageable for our SOC at scale, and our customers are not getting attacked or like compromised very often. So it seems like right now we kind of have a good system.
Can I add a little follow-up to that? Like I'm still curious, signal to noise, and you're doing very, very good with all signal and less noise. How important is curated data? Like, we've talked about a lot of things. Like, the cool thing about unsupervised is you can start now to look at all kinds of stuff, non-tag data, and get stuff from it. And you mentioned all it has to do is train on the environment to see what's normal. But then you have the question, was the environment in a normal state when it was trained, or was there an unbeknownst breach behind the scenes? And when we're talking about LLMs even, you have a crap load of internet data, and maybe 85% is probably true, fact-checked, or part of the encyclopedia or science, and the rest is junk. But the problem with curated data is to use this stuff. You really want data at scale. And how does someone curate data at scale? Is data curation somehow important to the growth of AI? Is there something we can do in our training to make sure that at least the training period is curated in some way?
Yeah. I mean, it's nice that cybersecurity is kind of a finite universe. It's protected from, I absolutely agree. The internet is like mostly false. And I would never dare.
I was probably being kind when I said 85%
yes.
true then. But yes, I agree.
But like, I think a good example, so this sixth sense anomaly detector. I said we give it, months and months of all of our customer data, but I only want it to learn on normal data, and so we have a few heuristics where we basically remove out. So suppose there's a customer and on Tuesday they had a detection, like a high or a critical detection somewhere in their network. I'm going to remove Tuesday and Wednesday and Monday for that whole customer from my training data. So I'm going to say something was up. Maybe it was just in one spot in that network. Maybe it was all over. I'm going to just treat that whole customer as compromised for 3 days and just remove them from my training data. And that's, like a way so that when I do feed this, okay, learn what's normal, it is actually super normal stuff. So that's data curation, and there's lots of choices you can make and how to filter out.
Awesome. That's probably where the science comes into data science. Yeah. So really quick question, throughout this, you kind of talked about the evolution of how AI has gone from basic LM and algorithm growth like nearest neighbors to random forest. We've talked about neural networks. You've talked about how LLMs are using transformers. And from even a neophyte's perspective, the evolution of all this seems to be so fast. Is that advancement, is there still new advancement that is yet to be discovered as fast, or are we kind of at a plateau where, yes, the AI companies are talking about it, but they haven't really pushed the back end advancement much lately?
I think there's no plateau in sight. The way that the closed source and open source communities are bouncing ideas off each other, and like new algorithms come up for like a faster way to implement attention, or like this slightly optimized thing, and then everyone starts using it like a few days later. There's so many, some of those are small improvements, some of those are massive improvements. So that gives me hope. The other one is just like this whole obsession we have right now with transformers, I think is nearsighted, and there's other stuff out there too. I could go on and on talking. There's one Japanese tech company called Sakana. I don't know how you say it, but
Sakana means fish, by the way, so it might be Sakana.
Okay. Maybe they're inspired by fish. They're inspired by biology. They approach this like, I was talking about like wiring the neural networks. We're just barely starting to do interesting creative stuff there, and this Japanese company Sakana AI is like, what if instead we like made these neurons, and so like the capacity for the model is captured in the patterns of like synchronous like activations, not in individual activations, but in the patterns of the activations, and they just like rewire a network and train it. Like, oh yeah, we can do that too. Now it also learns the internet, and it's just like that much more like our brains. So there's just so many different ways that you can push the boundary of, and then there's also just like more traditional ML that has nothing to do with neural networks that like there's this area called topological data analysis that I used to be in, where there's algorithms that have not been put into, as far as I know, much use in industry, but they are like cutting edge mathematical algorithms for analyzing data and extracting insights and stuff. So I'm very excited about
That's awesome.
So you're basically saying it's like it's probably in its infancy in technology, even though it started in the 60s, 70s, and there's a lot to come.
Right.
Exciting.
Yeah. That's my opinion.
That's cool. So I know we're unfortunately running out on time, but I wanted to like end with one question, maybe for some of our listeners or other folks, where it seems like, up until like a couple of years ago, we told everyone, hey, go get a computer science degree and you'll go get a job. And then now it seems to be, okay, maybe you got to do something AI focused to be able to get a job. Your field seems, at least from my perspective as a fellow nerd, super interesting. And I'm curious, like, what kind of advice you would give a student maybe that was wanting to get into your field of data science and even like cutting edge AI and machine learning data science. Like, what might you tell them?
So on a practical level, I would say just use as much AI as you can right now and get comfortable with it. Like, get Gemini on your phone and start using it, and just realize this is insanely amazing. And like, if someone tells you, oh yeah, I was disappointed in it, just like wait a couple weeks and try again, because it's changing so fast. This will, superpower your productivity and your ability to learn new things. I mean, I'm like, it just blows me away how much I can just learn so much new stuff so much faster. I think about ways I can add, the AI to my, like I have an AI browser called Dia that I love using, where you can like chat with web pages and stuff. I think that's kind of the future of browsing. Just really going to change everything. So we're in such a fortunate, I mean, this is not to be too preachy about it, but this is a revolution and it's not going to stop. And like, it's time to embrace it. And especially if you're interested in going into the field, you need to have these AI tools under your belt and familiarity with them, because whatever the future of the workforce looks like, this will be crucial skills. And that's sort of the practical one. And then an impractical one, I think being a contrarian is probably my secret to success. Just a very go into every situation and disagree with it. Seems like a weird piece of advice, but it's like
skepticism, common insecurity.
Yeah. If you talk about being a hacker, I think you have to be obsessed with things and you want to be a bit of a contrarian, and just even a self-contrarian, ask yourself, well, what if I'm wrong? I mean, how often do you ask yourself that? How often do we ask ourselves that? It's such a powerful tool, skepticism, questioning everything, and just approaching everything. I mean, I honestly think if something, once something becomes popular, it's bad. It's a bad idea. Only the bad things become popular. Look at the things variational autoencoders that are not popular, but lo and behold are pretty cool, Hardcore.
That's good advice.
I feel like I know the answer to this 30-second just hot take question. AI, save the world or kill humanity? What's your hot take? You just said it was completely necessary. So think 30 years from now, has it saved the world or killed humanity?
I'd probably save the world. Yeah, I would vote for the world.
Yeah. I agree. I think it's up to us to make that happen. But
I'm not convinced.
Yeah, it has a lot of power, like a lot of technologies humans have used. But I can see a scenario where we use it. All the technology so far has doubled our lifespan. This is scary. It has potential to really disrupt. It is a revolution, whether that's a good or a bad one. But cool. I like your hot take. I hope it's true.
I do hope it's true too. But I guess we will see. But anyways, Luke, thank you so much for hopping on. This was really interesting. I learned a ton, especially about drumming through and the differences in drumming from Northern and Southern Indian cultures. So I'm gonna have to go check some more of that out.
I don't know any about that, especially if you say they have complex rhythms. And if we have any big technical AI stories, now we have an internal guest we can have to come and advise us on them.
Yeah. So thank you again, Luke. Appreciate it. Thanks everyone for listening. As always, if you enjoyed today's episode, don't forget to rate, review, and subscribe. If you have any questions on today's topics or suggestions for future episode topics, you can reach out to me on Blue Sky at itsmark.me. Corey's at SecAdept, and the both of us are still on Instagram at WatchGuard_technologies. If you have any questions for Luke, kick him over there too, and we will bring him back on to chat about it. So thanks again for listening, and you will hear from us next week.